Hello everyone, this video is for section 11.9, which is all about representing different functions as power series. So in the last section, 11.8, we introduced the idea of power series. So let's just revisit that real quick. This is really how we should be thinking about power series. So let's say we have a series that we're used to from sections 11.2 through 11.6 or 7. We just have this series C sub n for n from 0 to infinity, like our normal series where these Cn's are just numbers, right? Okay. We ask if this series converges or diverges, and when it converges, it should converge to just a single number. Okay, so there's no variable in here, right? If this series converges, it just converges to a single number. That's it. It doesn't change. Then in 11.8, we started playing with the idea: what if we introduce a variable, an independent variable like x? Okay. So let's look at that. So let's look at our power series, right? This is the standard form of our power series. We have these C sub n's, which are these are still numbers, okay, but still just real numbers. But then we pair it with this thing, x minus a to the power n. That a is also just a fixed number, but then we have this independent variable x, and we have this power n here, hence power series. Okay. So this is our standard form of a power series. And just like with the previous series, they might converge or diverge. And in the last section, we kind of saw how to figure out where they converge, right? They're going to converge maybe at just a single point, maybe a finite interval, maybe an infinite interval. Okay. So this power series can converge or diverge. And think about what's happening where it converges. So let's assume our power series converges on some finite interval. We'll call that a. We'll call this a minus r to a plus r. So let's assume our power series converges in this interval. Okay, what's going on inside that interval? Well, I can pick any x I want in here and plug it into my power series, right? And my power series is going to converge there, and it's going to spit out a value for that x. Okay, so in that way, what am I doing? I'm plugging in x's and for my inputs, and I'm getting different outputs. What does that sound like? It kind of sounds like our idea of a function, right? The whole idea of a function, if you remember, like a function f of x, you plug in an x and it spits something out. It's basically just an input-output machine. Okay, and we see that when the power series converges, it's doing the same thing, right? I'm plugging in some number for x, and then I add up all these terms, right, in the series, and it spits out a number, okay, for that particular x. And then I plug in a different x, and it gives me a different output, right? So that's my usual idea of a function. And in fact, we can just label this thing. We have a power series here. We could just label that g of x and call that a function called a day, right? This is a function. So just call that function g of x. And sometimes we'll see that. Sometimes we'll be given a function, like we'll be told, okay, g of x is equal to some series, some power series. And then, maybe you'll be told, find g of 1. Okay. Well, what do? You take 1 and you plug it into this and you look at the number. Okay. So these things are series, or these power series are functions, and we can deal with them like functions on their own. But what's interesting about power series is that sometimes it's not just like, sometimes when we have a power series, the function on the left-hand side is something we recognize. We can write it as something more specific than just g of x. What do I mean by that? Okay. Think about this series. This is the geometric series, right? R to the power n. And there's no x's, right? This is just our standard like 11.2 through 11.6 understanding of a series. Okay, so I have a geometric series, R to the power n. And remember, this converges when absolute value of r is less than 1. And when it converges, it has this sum. Okay. And then in 11.8, I believe we briefly looked at this power series, x to the n, right? And it's very similar to this series up here. Okay. It's going to converge when absolute value of x is less than 1. So it has this interval of convergence from -1 to 1, right? The series converges for all these values. And when it converges, okay, this power series is equal to this, okay? So on that interval -1 to 1, this power series, x to the n, is the exact same as this function, 1 over 1 minus x. So we can call the power series x to the power n the power series representation of 1 over 1 minus x. Okay. And it turns out that other well-known functions have power series representations. Okay, like the basic trig functions like sine, cosine, etc., e to the power x, ln of x. These things all have power series representations, meaning like if I have sine of x on a certain interval, okay, instead of writing sine of, I could write this as a power series. I could write this as a to the n, x to the power n. I forget what these constants are. We're going to solve for these these coefficients. We're going to solve for these in the next section. But basically what happens is I can rewrite this sine of x as a power series. I can find a power series that represents my function. You might be asking, okay, why do we bother doing this? Isn't sine of x a lot easier to work with than, whatever that series ends up being? For something simple like this, yeah, the function sine of x is easier to work with. But we're going to see some really cool applications, and you'll see them again if you take differential equations. A function like this, okay, e to the power of x squared. We can't integrate this, okay? We can't integrate that directly. But if I turn it into a power series, maybe then I can integrate it, right? Maybe, it turns out that I can write this e to the x squared. I can write this as a power series, right? And then, well, I can't integrate this directly, but maybe I can integrate that power series, okay? And there's a similar idea for differential equations, things like that. Sometimes it's easier to work with these power series. Okay. So there's a very technical and general way to find power series for functions. Like if we have a differentiable function, we have a nice general way to find its power series. And we're going to get to that in section 11.10. But for now, what we're going to do in section 11.9 is we're going to start with one power series, one kind of simple power series, and then we're just going to modify it to get the power series for a bunch of other different functions. So let's start with that same power series we were looking at a moment ago. This power series x to the n. Okay, this is the power series centered at 0, right? For the function 1 over 1 minus x. Okay, and remember this is convergent on this interval, -1 to 1. But what if let's modify this? What we're going to do is we can modify this power series to find the power series for other functions that are similar to this, 1 over 1 minus x. That's the idea of what we're going to be doing in this section. So let's say I want to find the power series for x over 1 minus x. How can I do that? Well, note that x over 1 minus x is just x times 1 over 1 minus x, right? And what do I know? I know how to find the power series for this thing in parentheses, right? Right. So let's just, in this line, let's just replace this thing in parentheses. Let's just replace it with the power series, okay? We know that power series is that, x to the n. And then I'm multiplying by x, right? And it turns out I can just take this x inside the power series. I'm going to treat it like a constant. Okay, so I'm going to take it inside the power series, and then I'm just going to simplify. Okay, so x times x to the power n, that's the same thing as x to the power n plus 1. So I see that my power series for x over 1 minus x is equal to x to the power n plus 1. Now, is this power series representation should only be valid on some interval, right? The interval of convergence. Are the interval of convergence, the intervals of convergence the same? Is the interval of convergence for this function the same as the interval of convergence for this function? Not necessarily. So if we're given a question like, find the power series representation for this function and find its interval of convergence, okay? Even if we modify, an existing power series like this to get a new power series, we still need to find the interval of convergence again for this function. Okay. So how would we find the interval of convergence? Let's see, this is our power series, right? Let's find the interval of convergence for that. And it's the same exact thing we did in section 11.8. It's either going to be ratio test or root test, right? So let's do ratio test on this thing. An plus 1 over an, well, that ends up being x to the power n plus 1 over x to the power n, absolute value, okay, which gives me absolute value of x, right? It simplifies as absolute value of x. And for my series to be convergent, okay, the limit of this an plus 1, which is this, that needs to be less than 1. So in essence, I want absolute value of x to be less than 1, okay? So I get this interval, and I know my series is going to be convergent everywhere inside that interval, right, between -1 and 1, but I don't know what's happening at the endpoints. So again, I need to test those endpoints individually. So I plug in x equals -1. Okay, I see my series diverges. Remember, I'm plugging that value in here for x. So I plug in x equals -1. That's going to diverge just because it's going to keep oscillating. And then I plug in x equals +1, and my series is going to blow up to infinity. Okay, so again, it diverges there. So both my endpoints diverge. So I see that my interval of convergence is just -1 to 1 with parentheses, which is the exact same as my original power series' interval, but that won't always be the case. And if I wanted to, I could find the radius of convergence. That's 1. Okay. So let's do a similar problem. Again, I'm with like 99% of my problems in this section. I'm going to start with 1 over 1 minus x. I'm going to its power series x to the power n. Okay. I'm memorizing this essentially. I'm starting from knowledge of this. Okay. I'm taking this for granted, basically, this power series over here. Okay. And I want to modify this power series to get a power series for this thing. Okay. So the question is, okay, how is 1 over 1 plus x, how is that related to 1 over 1 minus x? Okay. And it might help to think of 1 over 1 minus x. Think of that as 1 over 1 minus x in parentheses. Then what's 1 over 1 plus x? Okay. Basically what I want is I want to get this to be a minus sign. How can I do that? Well, I can rewrite this thing as 1 over 1 minus negative x, right? And on one hand, okay, I know this power series, right? That's equal to this thing, x to the power n. Okay. Well, if 1 over 1 minus x equals this, what should this be? The only difference is, okay, here I have positive x, here I have negative x. Okay. So maybe I should expect that the power series for this thing would just be negative x to the power n. And it turns out that, yeah, that's exactly what's going to happen. So basically, this is just the same work I've done. So I note that 1 over 1 plus x, that's the same as 1 over 1 minus negative x. Okay. Then we have our power series. And I'll skip the work for finding the interval of convergence, but it should end up being -1 to 1 again, without the endpoints included. You guys can do the interval of convergence, find that on your own, and double check me. So in general, okay, let's say I have c, I'm given the function like c over 1 plus or minus, something in parentheses. So this stuff in parentheses, it could be x, it's going to be something with x involved, right? It could be x, could be 4x, it could be x cubed and so on. Okay, so I'm leaving it kind of blank, so you just have the most general form of stuff. And then this c on top, that could be, it's not necessarily constant, maybe I should say like cx or something like that, or cx to the n. Okay, this stuff on top could be complicated, so let's leave it as this. So how would you find a power series representation for that? Well, in this section, it's all about relating back to this function. So basically, we're going to try and get this into a form that looks like 1 over 1 minus x. Okay, and it's not going to be exact, but it's going to be close enough to work with. Okay, I'm going to just leave this as c up top. So what do I do? First, I would factor out this c to the side. Okay, I'll bring it up to the side, so I have c times 1 over 1, and let's do this a bit slower. Okay, so factor out that c to get this. Okay. And then what am I going to do? I want a minus in here. Remember, I'm relating this back to, 1 over 1 minus x. So this thing in the middle, I want to be a minus. Okay, so maybe I'm given a plus, or maybe I'm given a minus. Okay, if I'm given a minus, I don't have to do anything, right? But if I'm given a plus, I need to change that to a minus, and then to balance out, there needs to be a minus in there. Okay, so that's kind of what I had going on in here. Okay, if I'm given a plus here, that needs to be a minus, and there needs to be a minus. If I'm given a, yeah, so we need to modify the sign in the middle, is what I'm saying. I believe how I had it written before is like this, which is kind of confusing notation. It actually makes sense if you can follow it. Okay, so just know that if you need to explain a little bit more, factor out the c and change the thing in the middle to a minus. And then you got to change this stuff inside correspondingly. Okay. Okay. So once we're here, we should be able to write a power series for this thing, right? And that's kind of what I've done here. I've written for a power series for the stuff inside parentheses. And this parentheses here is going to be this parentheses here. Okay. And then I still have my c outside. Okay. I'm multiplying by my c. Okay. Now the next step 3, would be to take this c inside the series and then simplify everything. Okay. And then that should be our series, our power series representation. But then step 4 is usually where I ask to find the interval of convergence as well, and maybe radius of convergence. So that would be step 4. Okay, so these are very general steps, and they might not make sense right at this moment, but let's see an example and let's see them applied. So let's find the power series representation for x squared over 1 plus x cubed. Okay, so let's look at step 1. First, we need to what? We need to factor out the stuff in the numerator and then get this sign. We need to get this sign to be a minus, all right? So we need to factor out this x squared and then get that to be a minus. Okay, well, let's factor out the x squared. Okay. So first I have x squared times 1 over 1 plus x cubed. Okay, now let's get that sign in the middle to be a minus sign. Okay. I'm going to change that to a minus, and that means I need to have minus x cubed in parentheses here. Okay. Now forget about the x squared for a minute. This stuff in parentheses, that's similar to 1 over 1 minus x, right? Okay. The only difference is I have negative x cubed instead of x. Okay. So I expect the power series, okay. Remember, 1 over 1 minus x gives me x to the power n, right? So 1 over 1 minus negative x cubed, that should give me negative x cubed to the n. Hope you can see that. Okay. So this power series in parentheses should be negative x cubed to the power n from 0 to infinity. Then I have x squared out front. Okay. And all right, so now we need to simplify and bring the x squared inside. And when I say simplify, maybe we need to do some simplification first. Okay. So let's kind of deal with this stuff in parentheses a little bit. Negative x cubed to the power n. How can I rewrite that to make my life a little bit easier? Okay. Well, I could split all this up. Okay. So negative x cubed to the power n. See if you can follow. That's the same as negative 1 to the power n, right? X to the power 3n. Okay. If that's a little confusing, just review on how raising exponents to exponents works. That's all we're doing, right? So for example, 4 to the power 2 to the power 5, right? That's the same as 4 to the power 2 times 5. And if I have like 3 times 4 to the power 2, okay, to the power 5, that's the same as 3 to the power 5 times 4 to the power 2 times 5, right? So that's all that's going on here. All right, now I got x squared, and this stuff inside the parentheses is now simplified. Now let's bring the x. I want everything inside my series at the end. Okay, I want everything inside the summation sign at the end. So let's bring that x squared inside. Okay. So I got x squared times x. Oh, x to the 3n. Okay. Now I just need to combine this x squared with this x to the 3n. How could I rewrite that? That's the same as x to the 3n plus 2. And this is about as simple as I can make my series. So I would stop right there. Well, for writing the series, right? So that would be my series. That's my series representation. And the next thing I need to do is find my interval of convergence, radius of convergence. So finding interval of convergence, radius of convergence. I hadn't planned to do that for this example. I'll leave you guys. I'll let you guys do interval of convergence, radius of convergence. We'll move on. So up to this point, we've really just done simple modifications of 1 over 1 minus x. Okay. Maybe we factored this. Maybe we had a c up here that we factored, right? Factored out. Or maybe we had a sign that we needed to change, right? But that's pretty much all we've done so far. Okay. Now let's develop a couple new methods. Okay. And these new methods are going to rely on differentiation and integration. So let's say I have 1 over 1 minus x, okay, and that we're saying is equal to this power series, x to the power n, on the interval negative 1 to 1. Okay. Now remember what that power series is, right? That's just 1 plus x squared plus x cubed, and so on and so on. Okay. That power series, this thing, I could kind of think of it as a infinitely long polynomial, right? It's a polynomial that goes on forever. And polynomials are differentiable, right? There's nothing tricky going on there. We can differentiate these things. So I kind of hope that this infinitely long thing is also differentiable. It looks like it's differentiable, right? So let's just differentiate each term and see what happens. So why are we doing this? Remember, if I had a polynomial like 3x squared plus 7x to the 4th plus, x to the 5th, and I wanted to take the derivative of that, right? It's pretty easy. I just take the derivative of each term, 6x plus what? 28x cubed plus 5x to the 4th, okay? So I got this polynomial. To take the derivative, I just differentiate term by term. That's how I hope this works as well. Okay, I'm not going to necessarily show that this is how it works, but I mean this is how it works. Okay. When it's differentiable. So don't worry about why it works. Just assume it's fairly intuitively clear, right? It seems obvious that it should work like this, right? So don't worry about trying to prove it or anything. Okay. So it looks like the derivative of this power series should be this, okay? And how can we rewrite this power series? Well, it turns out that's just n to the power x n minus, or excuse me, n times x to the power n minus 1, okay? And this notation might be a little unclear at first, but remember when we have forget about series and stuff for a second. If I have x to the power n, right, and I differentiate it, what would that be? It would be n times x to the power n minus 1. Okay. So if I have a power series, what is a power series? And let's look at the simple power series. Let's look at x to the n. If I differentiate this, I have all these terms that look like this. If I differentiate all the terms, and then add them together, I should just end up with a series that looks like this, right? I just bring the n down, and then this loses a power, okay? So it's just power rule infinitely many times. Okay. So I'm saying that it looks like this power series is differentiable and its derivative looks like this, okay? And on the other hand, well, this function, that's differentiable, right? So if I'm starting with this function, I differentiate this side, that's the same thing as differentiating this side, okay? On this side, I end up with what? I end up with n to the x n minus 1. And on this side, what do I end up with? Well, let's see. We end up with 1 minus x to the power negative 2, right? So it looks like if I'm asked what the power series for this is, and I can spot that, okay, well, this thing is the derivative of 1 over 1 minus x. Well, then what I do is I find the power series for this, and then I differentiate this power series, and that should give me the power series of the derivative. Okay. So mouthful there. And then again, we should find the interval of convergence and radius of convergence. So this is my work for finding the interval of convergence, and it ends up being negative 1 to 1, just with parentheses again. Try that on your own as well. All right, so that's kind of a little example of where we're going with this. Now let's state the theorem, and this theorem is in your book, and it's stated without proof. So again, don't worry about the guts of why this works. It just works. So let's say we start with the power series C sub n x minus a to the power n. And let's say this radius of convergence, this series has a radius of convergence greater than 0. Okay, so this could be this power series could converge everywhere, or maybe it's just a finite interval. But we're saying it's convergent at more than just a single point. Okay. Well, think about the power series. Okay. So let's say the power series is this, which we could write as c sub 0 plus c1 x minus a to the power 1 plus c2 x minus a to the power 2, and so on. Okay. Well, on that interval, or excuse me, yeah, on that interval of convergence, that power series is going to be differentiable, and we're going to take the derivative just like we would with any other polynomial. Okay, that's what this is saying that the derivative is just, exactly what we would expect. What's the derivative of this part? The derivative of that part would just be c1. What's the derivative of this part? Well, that would be 2 times c2 times x minus a, and that's exactly what it is. Okay. So the derivative behaves exactly like you would hope it would. Okay. And the derivative behaves nicely, and so does the integral. Okay, if I want to integrate my power series, okay, let's kind of C0. Let's say my power series is Cn x minus a to the power n, right? Which is equal to C0 plus C1 x minus a plus C2 x minus a squared, okay? What's the integral of that? Well, if I integrated term by term, I'll get C0 plus, C0 times x, right? And then C1 x minus a to the power 2 over 2 plus C3 x minus a to the power 3 over 3, right? Now I would have a bunch of terms, and then I would have this constant of integration at the end, right? Plus, some constant of integration. So how can we rewrite all this stuff? Well, that is the same thing as the series starting at 1. No, excuse me, starting at 0. It's the series starting at 0. Let's see. Cn x to the n plus 1 over n. Okay. And that makes sense. If I'm starting with this series, Cn x to the n, and actually this should be x minus a power n, right? So if I'm starting with the series Cn x minus a to the n, okay, just think about if I just had this term and I integrated it, what would that look like? It would become Cn x minus a to the power n plus 1 over n plus 1, right? Okay, so if I have a bunch of those terms in a series, okay, I end up with those. Okay. All right. Let me go back to, so that's our theorem, okay? The radius of convergence, okay, so when I integrate and differentiate, it does not change my radius of convergence, okay? The radius, if this series has radius of convergence r, then its derivative will also have radius of convergence r, and its integral will also have radius of convergence r. The endpoints might be different, okay? So we still need to check the endpoints individually, but the radius of convergence is still the same. So that's the theorem. Let me circle back to point 1 here about derivatives. Okay, so notice that my original series, okay, what was my original series? My original series is this thing. Okay. I have c sub n, x minus a to the power n, and notice this is starting at 0, n equals 0. Okay, now look at the derivative. Okay, when I take the derivative, I end up with this series, and it's starting at n equals 1. Okay, why? Okay. So this is my original, okay? And remember what that is. That's the same thing as C0 plus C1 x minus a plus C2 x minus a squared and so on. I differentiate. Okay, what happens to this first term that's just a constant? It just gets knocked out, right? It's 0. Then I have C1. Then I got 2C2 x minus a plus blah, blah, blah. Okay. One way to think about it is you just ignore this sign and try and write a formula for the series. And if you do that, let's see, you could write this as Cn x minus a to the power n, starting at what? N equals 1. Okay. Does that make sense? And then, oh, this would actually be x n minus 1. Okay. So, and that's what we ended up with, right? So that's really just how you should think about it. Just that first term, that first constant gets knocked out when you differentiate. So instead of starting at 0, you're starting at 1. That's essentially what's going on. All right. So that's the theorem. Now let's see how to apply the theorem. Okay, so here's some steps again. So let's say we're given, and there's going to be kind of 2 scenarios. Okay, I'm going to give you kind of 2 sets of steps, one for kind of number 1, one for number 2. So let's say I'm given a series like C over 1 plus blank. Okay, that series, this thing. Okay, I'm keeping it very general right now, but that's essentially going to be a derivative of something that looks like this. Okay, and I should be able to find at this point. I know how to find the power series for this thing. This is just my like my factoring and my changing the sign in the middle. Okay, so I can usually make a power series for this thing. Okay. Okay. So I know the function I'm given is like the derivative of something nice. Okay. So I'm gonna figure out what that something nice is. Like it's kind of unknown at this point. I'm gonna figure out what that thing in parentheses is. Okay. And then I'm gonna find, and how do I do that, first of all? All right. I'm starting with the assumption that, okay, my function is the derivative of something nice. Okay, so I need to figure out what this is. I need to get rid of this derivative sign, right? Okay. How do you get rid of derivative signs? You integrate. Okay. So if I integrate both sides of this equation, let's see. I know what this function is, so I can integrate it. So I integrate it. And what's happening on this side? The derivative sign and the integral sign are going to cancel out. Okay. And I'm just going to be left with my function. Okay. Think about it like this. What we're doing is I'm saying that my function is equal to f, is equal to the derivative of f. Okay, and let's just leave it as f, kind of representing an unknown. I want to figure out what f is. Okay, so what do I need to do? I need to get f by itself. So I need to cancel out the derivative, and to do that, I just integrate both sides. Then you find the power series for f, right? So at this point we have, okay, we have something on the left side. We have the integral of our function, which we can solve, right? We have that integral is equal to our function f. Next thing we're going to do is we're going to find the power series for f, right? We should be able to find the power series for f. And we're going to do that by comparing it to 1 over 1 minus x. All right. So now at this point we have, okay, that we have a function, all right? Okay, this is the thing we started with. We integrate it, and we're saying that's equal to f. And then we should be able to find a power series for f. Okay. All right. Now, remember, so this is the power series for the integral of the thing I started with. How do I find the power series for just this without the integral sign? Well, now I need to get rid of that integral sign, right? So I differentiate both sides. Okay. So that sounded really confusing. I apologize, but let's again see it in action. So let's say I want to find a power series representation for the function 1 over 1 plus 4x, and then that denominator is all squared. Okay. If I just had this, or even this, I could find a power series just by comparing this directly to 1 over 1 minus x. Okay. When everything is squared, you can't do that, because there's no nice way to factor this thing to get it to match this or anything close to that. Okay. So what we have to do is think to ourselves, hey, this looks like it's probably the derivative of something that's like close to 1 over 1 minus x. Okay. We got to figure out what this thing is. Okay. So how do we do that? What I'm going to do, and let's, instead of just writing all these words, let's just call it f. Okay. So let's figure out what f is. How do I do that? I need to cancel out this derivative sign, right? So I'm going to integrate both sides. So really, this is our step 1. Step 2 is just integrating both sides. Okay. So what happens on the right side? The integral sign and the derivative sign cancel out, and I'm just left with f. And on the left side, well, I just have a integral, and I know how to solve that integral, right? It's a u sub, it's u equals 1 plus 4x. Okay, so du over 4 equals dx. And let's see, that integral ends up being 1/4. This should be the integral, I believe, right? And okay, let's say there's a constant of integration. That we can put that in there, but really it's gonna get totally canceled out and for this type of problem. Okay, we're gonna have to deal with this in the other type of problem, but let's just keep track of it for now. Okay, so this is my f. Okay, well let's write a power series for this, and it might help to write this in this form. Okay, this is the same thing as that. Okay, now I got a plus c. And really, we're just keeping track of this for formality. It's not going to be important. This stuff in parentheses, I can find a power series for, right? By comparing it to 1 over 1 minus x, okay? So try that on your own, okay? And if you have a little practice under your belt at this point in the lecture, you might see that the series, well, I'll just go through it step by step. I could write that as 1 over 1 minus negative 4x, right? Okay. So that should have the series negative 4x to the power n. So this should be my power series for my f, and I could bring this negative 1/4 inside. Okay, and simplify things. It should simplify as this. Double check me on that. But if I split everything up, it should simplify this like this once I bring the -1/4 inside. Okay, so I got this power series and plus a constant equals my function. Now, remember what we're saying, okay? We're saying that our function is the derivative of f. Okay, so 1/1 plus 4x squared is the derivative of f, and f is the same thing as that power series, so our function is the derivative of that power series. Really, it's the derivative of that whole that thing, right? Okay, so let's just take the derivative of that power series. First of all, what's going to happen to that capital C? This is just a constant, right? So when we take the derivative, that's totally going to get obliterated, which is why I was saying for this type of problem, it's redundant. All right, what about the rest? What's the derivative of this stuff? Okay. Well, I just differentiate term by term. Okay, I treat -1 to the power n plus 1. I treat that as a constant. Same thing with 4 to the n minus 1. The only thing I differentiate really is this x to the n. And what does that become? N to the power, or n times x to the power n minus 1. And now instead of starting that series at 0, I'm going to start it at 1. And that should be my power series. Okay. So it's a lot, but let's review what we did. Okay, we started with some original function that we want to find a power series for. And we're kind of assuming it's the derivative of something nice that we can find a power series for. Okay. First thing we do is we figure out what this function is. And we do that by integrating both sides. Then we're going to find a power series for that thing in parentheses. Okay. And then we differentiate the power series to derive the power series for our original function. So it's a lot. This section is fairly complicated. I'm going to do a problem video for this section and really just all the remaining sections. I'm going to do a problem video for. Section 11.9, this section is kind of, I feel like it's probably harder than the remaining two because you got to use all these weird tricks to find the power series. In section 11.10, we kind of find a new way to find a power series that's, I think, much more straightforward. But let's continue on with the tricks. So what if I have a power series, or excuse me, what if I'm given a function like ln of 1 plus blank, okay? Maybe 4x is in here, maybe 2x, maybe x squared, something like that. Let's leave it as blank for now. So I'm given a function like that. How do I find a power series representation for that? Well, how is this ln of 1 plus blank, how is that related to that one power series we know? How is that related to 1/1, minus blank or whatever? Okay. Well, this is the integral of something that looks like that, right? So remember ln of 1 plus x, that's just the integral of 1/1 plus x, right? And I can find the power series for this thing. Okay, so that's kind of our starting point for this type of problem. If I have an ln, I think okay, that's the integral of something I can find the power series for. Okay, so what do? I start by figuring out what this thing is, okay? And let's leave this as f, okay? So I'm assuming that ln is the integral of some function f I can find a power series for. I need to find f. Okay, So what do? I need to cancel out the integral, so I differentiate both sides. Okay, I differentiate both sides, and then I should be left, I should at that point know what my f is, okay? And step 3, let's find the power series for f by comparing it to that 1 over 1 minus x. Now, the next step, okay, I have a power series, but the power series at this point is for the derivative of my function, okay? So how do I find the power series for my original? I integrate both sides. And then in this type of problem, I'm going to end up with a constant of integration, and that's not redundant. And in this type of problem, we do need to figure out what that c is. Okay, so let's see an example. So let's find the power series representation for the function ln of 2 plus 4x, 2 plus 4x all being in parentheses. Okay. So let's go through our steps. I'm assuming ln of 2 plus 4x is the integral of some function f, and I'm assuming like I can find the power series for this f. Okay, so first step is, first thing I want to do is figure out what that f is. So how do I figure out what f is? I differentiate both sides. Okay. So on the left side, what do I get? I get 1 over 2 plus 4x times 4, right? And I can simplify that. I can factor out a 2 if I wanted. Let's go ahead and factor out the 2. Okay, 2 over 1 plus 2x. Okay. That is equal to, let's see, derivative of integral. I should just be left with f on this side, right? Okay. Step 3. Okay, so this is my f. I want to find a power series for it. So what's the power series for that thing? Now this is something I can work with easily. Okay, so what's the power series of this? Well, let's again kind of rewrite things. Okay, now remember I'm just comparing to this power series for this thing. So the power series for the stuff in parentheses should be this. And then I'm multiplying by 2. So bring the 2 inside and maybe kind of split all this stuff inside it. And that should be what I arrive at. Okay, so this is my f. And I'm saying, let's just rewrite what we're saying. I'm saying ln of 2 plus 4x. Okay, I'm saying, what am I saying? I'm saying the derivative of this thing is equal to that power series. And let's see, should that be, yeah. Now let's integrate both sides. So basically, if I integrate the left side, the integral and the derivative will cancel, okay, and I'll be left with ln of 2 plus 4x, okay, plus c equals what's the integral of this power series? I treat -1 like a constant. I treat 2 to the n plus 1 like a constant. What's the integral of x to the n? X to the n plus 1 over n plus 1. Okay. So that's my integral. And then I got a plus c over here. Basically what I'm going to do is I'm going to collect all my constants on one side, right? Like I could think of this as c1, and this is c2, subtract c1 over here, okay? And then just relabel them as a single constant. So I have one single constant. So let's clean this up a bit. Okay. Now this C, unlike in the previous type of problem, this C is very important. So it looks like this is the power series for my function. Okay. It looks like this is it, but I can't just ignore that C. Okay. I need to figure out what that C is. Okay. That C is going to be critical. So how do I figure out what that C is? What I'm going to do is I'm just going to plug a value in to both sides of this thing. Okay. So what would be an easy value to plug into the left side? 0. How about 0? So let's say I plug in x equals 0 to the left side. Okay. What would I get on the left side? I'll get ln of 2. And then if I plug a 0 into the right side, what do I get? Don't overthink it. If I plug 0 into that, right, the series is just going to be 0 plus 0 plus 0 plus 0, blah, 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 blah. It's all just going to be a bunch of zeros, right? And then I got the plus C. Okay. And remember, adding up an infinite number of zeros, that's 0. So basically what I have is ln of 2 equals 0 plus C. So ln of 2 equals C. So what does that mean? My power series for ln of 2 plus 4x is then this thing plus ln of 2. Okay. So I'll just write it as ln of 2 plus the series. And this would be my power series representation. And again, we would not need to find interval of convergence, radius of convergence. So here's some general guidelines. This will be the last of the material. And then really this section is going to be, I think you'll learn more from the problem video and doing problems on your own. But for now, here's some general guidelines. Let's say I'm given a function of the form a over 1 plus blank to the n, or whatever. Okay. This should be something I can solve for just by directly modifying this 1 over 1 minus x. Okay. If I get something like a over 1 plus blank and that whole denominator is to the power n, okay, that's going to be the case where I start by integrating this to find a function, find its power series, and then differentiate to find the series for this thing. Okay. So when you see something of this form, think our integration differentiation techniques. And similarly, when I see an ln, okay, that's also going to be an integration differentiation technique. What I'll say is, okay, in the homeworks and stuff, you might see some problems that don't really fit into anything we've seen. Like they might tell you, find a power series for arctan of n, right? So how do we find that? I'll go over this one in particular on the, because I'm like 99% sure this is on the homework or something like it. What we do is, this is going to be a differentiation integration technique. What we do is I say to myself, hey, this is the integral of something, right? This is, arctan is the integral of 1 over 1 plus, or wait, no, this should be an x. Okay. Arctan of x is the integral of 1 over 1 plus x squared, right? I can find a power series for that, right? What is the power series for this? Okay. Well, this is just the same as, okay. So the power series should be, okay. And then if I integrate that power series, I should get the power series for this. So I'm going kind of fast on this one and skipping some steps. If you can follow, great. If not, this is just a preview. I'll be going over this one in more detail on the problem video. Let's see, this will be something like this. So even if we see something, you know, kind of unfamiliar like that, maybe we can still compare it to something that we can easily find a power series for. So that's all for 11.9. Expect the problem video soon.